All right. Hi, everyone. Welcome to today's seminar. So I'm delighted to introduce Eve Vavagiakis, who's tuning in from Duke University, where she's an assistant professor working on instrumentation for cosmology and astrophysics, in particular on observations of the CMB. And that is what we're going to hear about today. So, Eve, do you want to share your slides and then you can get started?
Yes. Okay. Thank you very much for having me. Yeah, I have never been to Australia, but it's nice to virtually visit. And I hope you forgive me if I misspeak. It's 9 p.m. and I'm starting to fall asleep, so this will be good to keep me up. I'm excited to talk with you all about some recent ACT results, specifically some DR6 results. Maybe you've tuned into the webinar on those just last month, or perhaps you know about the exciting first light announcements from the Simons Observatory, so I'll touch on those as well as discuss the CCAT status, which is also very exciting as the telescope is being assembled at the site for the very first time. So these will represent upcoming observations of the millimeter and submillimeter sky. And this slide is kind of excite by overwhelm is what I say. The sky doesn't really look like this and our instruments are not to scale, but these are some teasers for what we'll be talking about today. So I wanted to note the language used in the Astro 2020 decadal survey, remarking on the explosion of arcminute-scale CMB data, which is opening new frontiers in measurements that had not yet been possible until we have this new high resolution and high sensitivity data sets to measure things like CMB lensing and the kinematic Sunyaev-Zel'dovich effect, which is otherwise a very small signal. And the only way we are getting there is through technological advancements that are rapidly developing our abilities to make these highly sensitive measurements across large areas of the sky. Here you can see some detector arrays, the Atacama Cosmology Telescope as it once stood, and my colleagues and I doing some in-lab work on various instruments. And now we're building these very large cameras to deploy increasing numbers of detectors in order to have unprecedented measurements for cosmology and astrophysics. So here you can see work being done both by me in the lab at Cornell during my postdoc on ModCam for CCAT, and also my colleague in the University of Pennsylvania working on the Large Aperture Telescope receiver for the Simons Observatory. So with these surveys, we're going to have unprecedented overlap with large areas of sky that have also been imaged in optical and many other frequencies to enable us to do new multi-frequency cross-correlation measurements to kind of open our eyes to these difficult to measure signals that we can only do statistically. So today I'm going to talk about the Sunyaev-Zel'dovich effects with the Atacama Cosmology Telescope and also touch on what we're excited to be doing with future surveys. And I'll discuss the status and some details and instruments for the Simons Observatory and for CCAT. Oh, there we go. So ACT is no longer observing, but this was footage from the site when it was. You'll notice how much more developed the site is now with the Simons Observatory. But this is just some beautiful drone footage of the 6-meter mirror inside this telescope that illuminated the receiver that is still providing us with data to be analyzed, even though we stopped observations a couple of years ago. You can see it right there inside of that instrument space. It had these 3 instrument modules or optics tubes inside of it. And ACT surveyed for a couple of decades across a number of frequency bands in the millimeter to study the cosmic microwave background. And we recently just released our DR6 results of primary CMB anisotropies, which you can see here in this kind of cartoon illustration. This is from my children's book on neutrino physics. So you might see some little neutrino friends that are not to scale and also not realistic. But here you can see an illustration of primary anisotropies. These were encoded in the cosmic microwave background about 380,000 years after the Big Bang, and we are still interested in studying them today because they hold such rich information about the physics of our universe. So the photons then traverse all of the later time forming structures, These encode secondary anisotropies, which I will also discuss today. These are including the Sunyaev-Zel'dovich effects before the photons are finally being captured by this, again, very not to scale telescope of ACT on Earth. So here you can see some survey footprints from data taken from 2017 to 2022 with advanced ACT receiver in ACT. These maps covered 98, 150 gigahertz, and 220 gigahertz. And you can also see some overlapping surveys. So here the ACT data is in the orange, and then surveys such as the Sloan Digital Sky Survey and Euclid Dark Energy Survey are in various colors. This gave us rich opportunities for cross correlations already. And later I'll show some survey maps, and you can see how we're going to extend the area on the sky with the Simons Observatory and with CCAT. But for ACT DR6, we covered about 19,000 square degrees to a depth of about 10 microkelvin arc minutes. And if you are interested in working with this data, it's available on the NASA Lambda server. There is also an interactive web atlas that has been published, and this really fun HIPS data set in Aladdin, which you can kind of surf through real maps from ACT and then overlay surveys like from Gaia, just visually on the sky. It's really fun to play with. So for more on the maps, I encourage you to look at this publication. And now you can just see what ACT has achieved as compared to Planck in terms of our resolution. With our larger mirror, of course, we can do better in terms of resolution. And so this patch of sky is 13 degrees by 7 degrees. And if you toggle to the ACT plus Planck map at 150 gigahertz, you see these structures just pop out in their vivid resolution. So I'll just enjoy switching back and forth, and you can see some familiar astronomical structures in this data as well. And so what you're seeing here are point sources, the bright red sources, and also potentially some galaxy clusters in these dark blue sources here. That's the Sunyaev-Zel'dovich effect, which we'll talk about in detail. So what have we been able to do with these excellent maps? Well, we have confirmed lambda CDM with now even more precise data sets and extending the measurement to even smaller scales. So here in the scatter plot, you see the power spectrum from the CMB. The topmost plot is the temperature power spectrum. I'm not sure how familiar the audience is with power spectra, but this is also a little graphic to explain it, where you are decomposing the primary anisotropy fluctuations in the CMB using spherical harmonics and then plotting just the intensity as a function of angular scale in the sky. And what we've done with ACT, because of our ability to access the smaller angular scales because of the increased resolution, is we just have more blue data points out here. You can see how beautifully they fit the gray line in the plots. The gray line is lambda CDM cosmology, which of course lambda being the existence of dark energy that is providing us our accelerated expansion in our universe, and CDM being cold dark matter. So we know that although lambda CDM is well constrained with CMB data sets, we have these current tensions in cosmology from our CMB measurements with later time observables like type 1a supernovae. Specifically, we're very interested in understanding the Hubble constant, which is parametrizing the expansion rate of our universe. And with the ACT data from DR6, we are still ruling out the high H0 values that would agree with, for example, the SHU's data set. Here you can see ACT in blue and this P-ACT data set, which combines Planck and ACT data in purple. And we are finding consistencies with DESI and also consistencies with other CMB measurements like SBT3G. And if you look over here in the landscape between S8, which provides a parameterization of the clumpiness of the universe, with omega n, which gives matter density, we see that this tension in S8 is a little bit less pronounced than the tension that we're still seeing in each knot. So if you're familiar with the cosmic distance ladder, I work a lot with Dan Skolnick here at Duke now. And if you ever are familiar with Dan's great work in the realm of Hubble constant measurements, specifically from later time observables, you might know in his profile picture he has ladders. And I was able to find out that those were specifically placed there because of the cosmic distance ladder. So when we are looking at later time observables like type 1a supernovae, we depend on the ladder to tell us that. So that's just a fun fact. With DR6, we also looked into constraining neutrino mass and probing the standard model of particle physics. We found no evidence for new relativistic species. We were consistent with standard Big Bang nucleosynthesis. And unlike some previous measurements with ACT data, which suggested perhaps there was a favoring of an early dark energy composition in our universe, we no longer find that to be preferred over a cosmological constant. So these plots are showing you constraints on the sum of the neutrino masses in which the inverted hierarchy is excluded at high significance, especially in the data set that has this contribution from the DESI baryonic acoustic oscillation information and favoring the normal ordering. Then here you can see the parameter space constraints with the sum of the neutrino masses and matter density, in which the PAC data sets are providing these highly constrained regions that are also consistent with previous measurements from the CMB and DESI. This is a plot kind of breaking down the allowed parameter space with various compositions of uncertainties on the measurement of H naught over here and H naught again over here, both compared to the SHOES allowed parameter space and this Chicago Carnegie Hubble program results that come from Hubble and JWST. And you can see that still we are not quite in agreement with these higher H naught measurements. And we also are not suggesting that all these wealths of models that were explored in this paper, something like 30 plus models, none of them are preferred over lambda CDM cosmology. We also had released some really beautiful secondary anisotropy work. These maps were put out several months ago now, probably last year. Time is just going too quickly for me. But these are showing a lensing mass map using DR6 data across nearly a quarter of the sky. Dark matter dominated peaks are in orange and voids are in purple. And this map is especially beautiful if you load it either in some kind of high resolution image that is not my screen share right now and kind of zoom in. It's really stunning what measurements of secondary anisotropies, which are encoded in the CMB much later than the time of last scattering right after the Big Bang, but they're influenced by gravitational potential wells in this case as the photons traverse further 13.8 billion years to us. Just how vividly we can map out that structure using this data set. So to no surprise, we found consistency with lambda CDM cosmology here as well. We also overlapped the mass map with, for example, the Planck CIB map and found that, as you might intuit, dusty star-forming galaxies live where the matter lives. So here you can see peaks and voids from the ACT data in white and black, respectively. And the colorful overlays are the Planck CIB map, showing nice agreement with those peaks and voids as well. We can also cross-correlate with luminous red galaxies, for example, from DESI, and a high significance of 38 sigma cross-correlation of this lensing mass map with these tracers found as an independent probe of structure formation that is still highly complementary to the CMB, that we are consistent with the early universe results, even from late time observables. So looking where the LRGs are, for example. There are also results from ACT showing a test of gravity with the Sloan Digital Sky Survey CMAS and low Z samples. So there's a lot of interesting work that I'll get into also in just a few minutes, combining these optical sources and luminous red galaxy tracers with CMB data in order to study both late time effects and secondary anisotropies, as well as constrained cosmology as well. There's a question on Zoom.
Yeah, I just wanted to understand what tests of gravity means. This is anomalous light bending.
I'm sorry, you were a little garbled. Do
Sorry,
you want to
what does
understand
tests of gravity mean? Is it just anomalous light
tests
bending?
of gravity? Right. So when we're looking at these late time structure formation, we can toggle things like the evolution of structure through general relativity over time and suggest other models such as MOND, for example. So the paper that was put out that I'm referring to here is not a MOND paper, but there are also upcoming results from ACT testing modified Newtonian.
The signature you're looking at is anomalous light bending or something.
Um, I, I don't know if that paper covers that specifically, but it's akin to this. So it would be an alternative theory to general relativity and ruling it out with ACT data.
Okay, all right.
Thank you. Okay, so now I'm going to switch to the Sunyaev-Zel'dovich effect, which we're also studying with ACT data. So in this effect, you have a CMB photon traveling largely undisturbed until a small fraction of them will interact with the energetic electrons that cluster into galaxy group and cluster halos, for example. That provides a kick in energy to the CMB photon, which shifts the entire blackbody spectrum of that photon, resulting in a frequency-dependent signal that gives you either a decrement at these higher frequencies, or sorry, lower frequencies, and an increment at higher. And I have this freeze frame because obviously I need it too. So at around 220 gigahertz, there is a null, so you don't see any shift relative to what you would expect to see from the CMB as you're looking through these halos. But then as you move to lower frequencies, you start to see this decrement. As you move higher, you see an increment. You can visualize that also in this plot, where the blackbody spectrum of the CMB in blue is pushed upwards due to this exaggerated amount of mass in a halo, resulting in this null at 220 gigahertz, and then the difference as described high and low. This Compton Y, shown here in the plot, is the way we parameterize this effect. It's a unitless number, and it represents the number of CMB photon scatterings times the energy gain per scattering event. You can also express it via math in this way, where you have your Thomson scattering cross-section, your line of sight integral, so you're integrating up all of the gas that you're dealing with, integrating over the number of electrons you have and their temperature. And this gives you a Compton Y measurement that's proportional to the temperature shift in the CMB. So you can use this in a number of ways. On the left and the right are two different thrusts you can take when you're looking at millimeter wave data sets. One thing you can do is identify clusters in CMB maps alone. So in this case, you just take your CMB map, you filter it in some way, and the high signal to noise objects pop right out, and you can catalog them. We have made the largest SZ cluster catalog from millimeter wave data with ACT, and we're about to improve it further with DR6. So do keep an eye out for a DR6 cluster catalog update from SC measurements. And then we are also, again, highly complementary with optical surveys. So in this case, we are targeting lower mass halos than would pop out with our filtering methods. And in this case, we use statistical methods using optical tracers, such as luminous red galaxy clusters, or luminous red galaxy proxies for the centers of clusters to snack and get an average. So this slide is on the identify cluster side, this advertising our expanded catalog with DR6 and showing where we are right now with ACT DR5 and blue points. Other surveys such as the South Pole Telescope have also been measuring SZ clusters and cataloging them. And we're going to see an extension and an even further extension of the Simons Observatory and CCAT that we're really excited about. And here's an image referring to that second approach where I stacked on about 23,000 luminous red galaxy tracers from the Sloan Digital Sky Survey and looked at the average signal associated with those halos. And we are excited about studying the TIC effect in these halos because we are using this as a tool to illuminate baryon content of the universe and pushing back into higher redshift since the SC effect is redshift independent. We can peer into galaxy clusters as they evolved over time, looking at feedback mechanisms and non-thermal pressure, the subgrid physics information pieces that are difficult to predict and are still poorly understood. And we can use that to feed back into our KSE measurements as well, studying not just the astrophysics of these sources, but also probing cosmology. So these, the Compton-Y signal is not solely associated with galaxy group and cluster halos, but in fact, you can map it over the sky at large. And we have done that last year with measuring Compton-Y over about a third of the sky with ACT data. And this map, again, is also just really, really pretty. So I encourage anybody to take a deeper look into it. We really are, thanks to our sensitivity now, able to illuminate even things like filamentary structures, which people are starting to study between halos. And so we can probe the distribution of baryons at large with this tool set and constrain optical depths of samples of interest, which will help us with our physical measurements in terms of just fundamental physics. So switching gears a little bit to the kinetic Sunyaev-Zel'dovich effect, instead of depending on the temperature of the gas, this is a Doppler shift of CMB photons due to the bulk motion of the gas. So in this cartoon, you can see a CMB photon coming in and interacting with a galaxy that is either moving towards us along the line of sight or away from us, and providing a blue shift in that photon versus a red shift. And this bulk motion is shown here in these equations, equating the temperature shift that you see in the CMB map to the optical depth of the galaxy cluster gas. Importantly, the Compton-Y measurement I have been discussing with the TSE effect is also sensitive to the optical depth of this gas, as well as to the velocity of the gas along the line of sight. So we can measure this in a wide variety of ways. One statistical approach is the pairwise KSE measurement. And in this way, you equate the measured KSE signal with the line of sight gas momentum so that these equations are not super important unless you're interested in the details. I can go into them more. I'm just going to flash through them now. You estimate the mean pairwise momentum of galaxy cluster pairs by deconstructing their motion or estimating it from the line of sight momentum that you get from your temperature signals, and then measuring the geometry at play with the Cij factor that comes from the redshift. So all you really need to know is your temperature, your CMB map, which we have from our ACT data, and your redshift information, which we get from spectroscopic optical surveys. This gives us a plot such as this. So I'll just try to build some intuition here for a moment. When you're looking at pairwise momentum, in this case, it's towards one another when it's at its most extreme dip here. And that's because at small separation distances, if we're plotting pairwise momentum on the y-axis, separation distance on the x, at small separation distances, we know that galaxies will be falling towards each other due to the attractive force of gravity. And so we can do fits to these data points that we get as we bin our many galaxy samples into these radius of separation bins, and then fit to that data. And what that fit returns is actually a measurement of our optical depth of our sample. So why are we interested in studying this? Well, we can use this as a probe of large scale structure. Any probes of large scale structure will be sensitive to the things that change the way that that structure evolves, such as massive neutrinos. So we can use this to constrain the neutrino mass sum and serve as an input to cosmological models. So in this simulation, you can see what it looks like in terms of structure formation on large scales when you have no mass in neutrinos versus some mass, actually an exaggerated amount of mass. And what happens is the neutrinos essentially wash out the overdensities and underdensities because they don't cluster down into those overdense regions as much. They travel relativistically in the universe at early times, smearing out some of the structure. And so if you look at the right-hand plot, I'm no longer plotting momentum as the function of separation distance, but instead velocity. So the dip has become a peak, but the story is the same. Structures are moving towards each other faster at smaller separation distances because of gravitational infall. And what you can see in this pairwise velocity plot is the sensitivity to the neutrino mass sum. So relative to no mass neutrinos in black, the peak velocity is suppressed when you increase the mass in neutrinos. And that's because with less high peaks, less overdensities, you would have less gravitational infall, so things are just moving slower. So we're very interested in constraining this with cosmology as an external input to particle physics, hopefully addressing potentially with neutrinos this antimatter asymmetry that plagues us as a physics community. We're also interested in dark energy and gravity, like we just talked about, tests of gravity, for example. So in this pie chart of the universe, this is my preferred format of a pie chart. We know that we are dominated by dark energy, followed by dark matter, and then baryonic matter, which we identify as us, is trailing far behind. We are just crust. And we can start to investigate this by looking into, for example, general relativity's growth index, providing checks on that, as well as looking to see if the dark energy equation of state parameter might be different than what we expect or changing over time. And in this spinning cube, you can just see how structure changes over time. This is something that we're interested in studying with new tools, such as the pairwise KSE estimator. And you can see how that curve might be sensitive to toggling those inputs as well. So towards this end, we have so far made the highest significance detection of the pairwise KSE effect yet at over 5 sigma. Other SZ, other KSZ measurement approaches have now gotten up towards 10 sigma levels, and we are going to be increasing this sensitivity with our upcoming data sets with DR6, which is exciting. And our optical depth fits are tracing the baryon content in these structures as well. And this plot is trying to build a little bit of intuition. At higher luminosity samples of galaxies, you have more massive galaxies, so a higher signal, but at a lower galaxy count, so your uncertainties are larger. Whereas on the other end, you have fewer of these galaxies, many more of these galaxies, but they're lower mass, and so the uncertainties are smaller since you have many more, but the dip is smaller. So it's kind of this trade-off. You would want as many galaxies as possible. You'd want them to be as high mass as possible. And the only way to really improve this measurement overall is to increase your sample size, because of course you can't just conjure up lots of high mass galaxies. But with DESI, we're expanding our source counts by an order of magnitude, which we're really excited about. And one question that I'm trying to address in my research is using the TSE effect as an independent measurement of optical depth to take us from this dip in pairwise momentum space, break the degeneracy, and get us to pairwise velocities. In that way, we can measure these cosmological items of interest. And one way I'm trying to tackle that is an empirical y-tau relationship, where with the same data set, I'm measuring both Compton Y from the TSE and comparing it to optical depth measurements from the pairwise KSE, and then comparing to existing relationships between these two, like from hydrodynamical simulations, to better understand the subgrid physics at play, to understand if we can use those as models to reliably break the optical depth degeneracy and use it to estimate the optical depth for pairwise KSE measurements. So we're working on that right now. And also some papers just came out doing this type of work in a slightly different way with the TSE effect being stacked, exploring dust emission. This is something that we are going to need to tackle for this y-tau relationship, for example, as well as a stacked KSE measurement. That's that order 10 sigma measurement. I said it's a now 13 sigma stacked KSE measurement, showing certainly now that the baryonic content of these structures is extended past the dark matter halos, which is exciting. I'm going to skip over this for the interest of time. If anybody's interested, I can go back and talk more about some upcoming measurements with the SZ effect and act, but I'm really excited to get to the survey portion of the talk. So I'm going to skip to that, and then we can get any questions at the end. So I'll touch on the Simons Observatory and CCAT. So the Simons Observatory is an array of new telescopes on Saratoga. This is the same mountain, same site as ACT was operating. So you can see this updated location with all the new infrastructure in place. I mentioned it would look a little different. I think it certainly does. You look at ACT old ground shield over here. ACT is gone. We're going to be repurposing this ground shield for a small aperture telescope. And then here you can see 3 small aperture telescopes, which have seen first light this year, and our large aperture telescope, which has just seen first light last month. And so here you can see just some fun photos. I couldn't help but take a selfie when I was there last year, helping to put some SAT infrastructure on one of the platforms. And then this is what our Slack channel looked like for a few years as people were installing things. So it says, we're here to install one of these small aperture telescopes in the platform and chew bubble gum, and we're all at a gum. And this was the exciting moment that the large aperture telescope receiver was lifted into the LAT. So the small aperture telescopes, or SATs for short, are designed to study the potential early universe inflation that everybody is really excited to understand better. They will field around 30,000 detectors between 30 and 280 gigahertz. And here you can see a picture of a SAT and a picture that the SAT took of a planet. Excuse me. And so right now we have 3, but we will soon have one coming from SO UK, which is exciting. And then SO Japan is working on one as well. So again, the smaller aperture allows us better access to large angular scales in the sky, letting us study B modes and try to constrain the tensor to scalar ratio, which will tell us about ripples in gravity early on and help us understand inflation. The large aperture telescope is what we are excited for arc-minute resolution images. That's going to allow for the fun toggle moments between Planck data and CMB data from the ground. It will field around 30,000 detectors at 30 to 280 gigahertz, and is the largest cryogenic millimeter wave camera built yet. You can see people with scale, or people for scale in front of it here. So I took a selfie of it in the high bay here, sorry, this is the instrument space on the telescope. Down here is the high bay at UPenn where it was developed. And you can see that only some of the tubes are installed out of the total 13. We currently have these 6 open here. And advanced Simons Observatory, which has been funded, is going to help us flesh out this receiver and field more detectors in order to take better sensitivity measurements at multiple frequencies. So we're excited for advanced SO to come. So here's another cross section that will allow you to see kind of what it looks like inside of this receiver. And these instrument modules are exactly the same size as the ones that I will show for CCAT, just for a point of reference and some foreshadowing. So here is again just a glamour shot of the LAT at sunset. Specifically for SD science, this is going to be transformative because our large survey across the sky is going to overlap with many more square degrees of optical surveys. So we are going to increase our tracers by many-fold across many different measurement approaches. We'll be able to pretty much best all of the ACT data that I had just shown you today and improve our SE cluster measurements as well as our TSC and KSC effect measurements. So I'm referring back to that Astro 2020 decadal survey. We really are going to start to see these advancements coming through in the next few years. And we finally are observing or have first light established in the LAT, which is exciting. We did that by installing our mirrors. Finally, we had a mirror debacle, but our mirror is now in. And so here's an image of what that looked like along with some excited faces the first day, and then what it looked like the worst day of the 2. Apparently it was very sunny and nice before this, and then fog rolled in, which is very rare. So the whole reason we are in the Atacama Desert is because it is one of the driest locations on Earth. It is a high elevation, 17,000 feet. It puts us above the vast majority of Earth's precipitable water vapor, but not on this particular day. But the mirror is in and it works well, so we're happy about that. Okay, switching gears to CCAT. CCAT is actually just a copy of the LAT. It just has improved sensitivity, or rather surface accuracy of the mirrors, so that we can gain some measurement capability at submillimeter wavelengths due to our higher elevation. So here's a video of the telescope as it was being tested. Oh no, sound. Okay, I'm not sure how to turn that off. Let me turn that off. Didn't have it before. I'm not going to show you that. It's just moving around. I'll drag it to a freeze frame. That's what I'll do. There we go. It moves around. It rotates on the support cone and it scans back and forth with this kind of housing that holds the mirrors. But CCAT is an international consortium of universities. It's led by Cornell, and this is essentially, again, a lat with better mirrors. And here you can see inside of the receiver cabin what a instrument the size of PrimeCam looks like. The large aperture telescope receiver, which you just saw, is a little bit bigger. And this is coming together now, finally, at the site. This is an old slide, and then I'm going to show you some very new pictures. So in this old slide, you see the foundation being poured for the telescope, see the site being just leveled for the first time, and you're also seeing the location of the CCAT site, Cerro Chajnantor, right next to Cerro Toco, but at a higher elevation. So we are now up another 1,000 feet. We're at 18,000 feet in elevation. This is giving us an exciting personnel challenge because we can only work a very limited number of days up there. We need very stringent health checks and exams to make sure people can safely go up to that high elevation. It's classified as extreme high elevation in Chile, and so the rules are different than even at ACT and Simons Observatory, where already you need to wear oxygen to work. So this is an exciting series of plots that I showed of the ship that was taking CCAT to Chile. It took a little Caribbean vacation. It passed through the Panama Canal, through the Miraflores locks. Then it finally arrived at the port, and then it hung out in the port for quite some time until it was able to dock. And now it's unloading. And so if you're interested in following CCAT updates, you can look at the CCAT website. There's a gallery that is constantly being updated now, which is really fabulous. But look how far the site has come. There's the support cone foundation, like I referred to before. And the road was also improved greatly. So the embankments here were added so that you don't fall off of the road as easily. And the telescope parts are so heavy that you actually need multiple trucks to pass off between on your way up, because the tire pressure changes so significantly from down at San Pedro kind of level all the way up to 18,000 feet in elevation, or 5,600 meters, that you need to change off trucks with different tire pressures in order to get this thing up there. Here's another image showing kind of the impressive steepness of the mountains you need to traverse. And here's another shot of the road, which I just think is really exceptional. It's very windy, and it's not for the faint of heart. I personally am very excited to drive on it. I hope I get to soon. So slightly less deadly now, and things were being taken up to the site. And this is the first touchdown of one of the crates from our telescope manufacturer, Vertex. So we're going to be putting this together and seeing first light next year, which is going to be fabulous. So PrimeCam is our kind of large aperture telescope receiver for CCAT. It's a smaller diameter receiver, can hold up to 7 of those instrument modules, but again, they're the same size. Each module can be targeted to specific science goals, including frequency of observation, as well as spectroscopic capabilities. So a couple of things that make this unique for CCAT that is not the case for the Simons Observatory is that our detector technology is going to be kinetic inductance detectors. This is exciting because it's the largest scale deployment of these detectors yet, and these are less mature in terms of technology. So we're really going to be seeing an advancement here if we can see this out on FEAST, the Fred Young submillimeter telescope. I should have introduced that as the name, FEAST. And also, we're going to have these spectroscopic modules. This one will have a FabroPro interferometer, for example, for probing the epoch of reionization. And we're also going to be fielding modules with spectrometer on-chip technology, which is going to be exciting. So here you can see me standing with some parts as they were being put together in Utah, in the US, and the manufacturer who made the cryostat chamber. And now it's finally delivered at Cornell. This is my PhD institution. And it's really thrilling to finally see it in the building that I worked on it on CAD in the same building. And so here are some students and my PhD advisor, Mike Niemak at Cornell, putting these things together. We have been installing some multi-layer insulation on it. Here you can see this is the 80K stage where some filters are installed. And then I was able to actually go and work on it myself. I don't think I might include those photos later, but it was really nice to finally get a hand on the thing. So here you can see the planned layout for the frequencies that the modules will cover in PrimeCam, with 850 gigahertz, our highest frequency channel being at the center, two spectroscopically enabled modules at the side, and then running from 220 to 410 around here, including 280, 350, and 410. And there are many science goals that I cannot get into today, but if you're interested, I encourage you to look at our science goals and forecast paper. Just a note on naming. We went by CCAT Prime for quite some time. So this is actually going to be called the CCAT Prime Science Goals and Forecast paper, if you look it up on the archive. We are now back to just CCAT. It's just an update for anybody who's tracking our name conventions. But we're going to be conducting both a wide field survey for CMB measurements, CMB foreground measurements, so basically measurements at higher frequencies that are highly complementary for the SO ladder survey. And this is also going to help us understand galaxy cluster evolution, feed into SC science, as well as potentially measure Rayleigh scattering for the first time, which would be exciting. And it's going to be the first continuous wide field submillimeter survey ever done, which has wonderful opportunities for cross correlations. We will also do these smaller field surveys, which will allow us to go after galaxy evolution, galactic polarization, and time domain science targets. So if you're interested in learning more, again, this paper is where to look. And then just harping on these cross correlation opportunities, we're going to overlap with the entire SO large aperture telescope survey, as well as with large swaths of Rubin observations. We'll overlap with all of ACT data and some other, of course, optical surveys like DESI, which we're currently working on and very excited about. And with CCAT, we're going to be doing the exact same fields. So it's going to be great. One thing that we can help contribute to is the search for primordial gravitational waves by reducing the bias on the tensor to scalar ratio measurements by improving our foreground measurements. So observing with 350, 410, and 850 gigahertz is all going to contribute to bias reduction, which is really the name of the game. And when we're looking forward towards planning for CMB stage 4, we need to account for this as well and figure out what the best path forward is to the unprecedented measurements of R that we're all looking for. So SC science is also very exciting with CCAT. We're going to be able to help understand CIB contamination, which is a real problem, especially even right now with our ACT measurements. You could see some of the dust and some of the postage stamps I had showed earlier. We're also going to overlap, of course, with SO observations, and we'll be able to conduct new relativistic SC measurements, even with the first year of early data science or early science with ModCam data, which I haven't talked to you about ModCam yet, but I'm about to. But here you can see some curves showing where existing data points are in terms of frequency space for the relativistic S to Z effect, and where our ModCam data would fall, filling this unique niche in frequency coverage. The relativistic effect is highlighted in this plot here, being this rainbow splitting in the thermal SC curve. And you can see some Simons Observatory bands in yellow, some bands for PrimeCam on Feast in blue, and then shared bands in green. So up here, you can see our great access and unique access to the RSC splittings up here, which is going to be great. So ModCam is a single module receiver. This is what's actually going to see first light on Feast next year. ModCam is being tested in the lab. This is some footage from when I was a postdoc working on some early stage cryogenic measurements. It has this DR off to the side design that enables rear swapping of the modules in a much more user-friendly way than PrimeCam will. So first, it's going to see a year of early science measurements on Feast. Then it's going to be an instrument module test bed for PrimeCam. So right now, our module tests of the 280 gigahertz module are ongoing. Here you can see us posing with the module when we first inserted it. And the first arrays are in testing. Unfortunately, I do not have much time today to get into detectors. I'm just going to fly through the detector content, but if anybody is interested in this room, I'd be happy to talk more about the module, but essentially it fields silicon lenses, optical filters, optical structures like Leo stops and blackout materials, and then some detector arrays in the back, finally 3, which will fields over 10,000 polarization sensitive kids read out through the back of the module and through ModCam. So yeah, I said I'm not going to get into it, but here it is. So our coupling technology is feed horns, and if people are interested in hearing more, I can talk about it. We're also doing some LED mapping, working closely with NIST to produce these detectors for the first time. And then our readout exists. I'm not going to cover this either, but the readout is currently being developed, and this is one of our main technological challenges to get up and running at scale for kids. Another fun video, this is us putting the module in for the first time. So this is one thing that we're currently working on is plans for doing this for PrimeCam. It's one thing to do it with no dilution refrigerator in the way. It's another when there are many sensitive modules and a dilution refrigerator in the back of the receiver. So we are working on that, and I'm excited to be building a module right now at Duke, working with the local machine shop in aluminum welding to work towards 410 gigahertz. Precision cosmology in action. We put this in using weight plates from Amazon, and then sometimes to add a little bit more weight, undergrad backpacks and coats. But it works. It's in, and it's currently undergoing optical testing. We have 2 arrays of the 3 installed right now. You can see Yi, a student I worked with at Duke, installing some foam filtration into the front of ModCam to sub out for some filters that we had made at Cardiff, which had some structures in them, as well as being very fragile and difficult to work with. So optical testing is going well. Here you can see some beam mapping underway. And I should have updated this slide. The pre-instrument readiness review actually concluded 2 weeks ago, and so we're working on incorporating the feedback from that in advance of our readiness review later this year. That will allow us to put this thing in a box and ship it to Chile, and then put it on the telescope in 2026. With that, we're very excited to pursue joint analysis with ACT-DR6, study foregrounds, study galaxy clusters, SC effect, dusty star-forming galaxies, as well as getting our hands on some data for galactic science, studying our own Milky Way, looking at transients, and characterizing our atmosphere from this unique site for the first time with kids. So we'll be starting that off in 2026 in hopes to optimize our approach for the wide field survey with PrimeCam. We'll be doing full wide field survey observations in year 2 plus. And there's a lot of details here if people are interested. So I'll stop here and take questions. To summarize, we are entering this new era of millimeter and submillimeter observations with the Simons Observatory and CCAT. We've seen some excellent ACT data constraining the physics of our universe with the best H0 measurement with ACT from the CMB, yet improved further with data to come. We're currently probing astrophysics with DESI, and we're awaiting the increased sensitivity, resolution, frequency coverage, and exciting challenge of data volume to come with these new experiments. We've seen first light with SO this year, and we're going to see first light with CCAT next year. And we're going to open up new windows at higher frequencies to ready us for upcoming measurements, including those from CMB stage 4. And here you can see my team and I putting together a dilution refrigerator at Duke. I like this photo because it looks like we're worshiping the dilution refrigerator. And here I'm just giving the gas handling system a good hug. So we're excited to study both detectors in the lab as well as cryogenic or cryomechanical interfaces. And work towards improving these instruments more even into the future, and as also contributing to analysis techniques, preparing us for this exciting new era where we're going to be systematics driven and excited for what's to come. So thank you very much.
Thank you. Yes, any questions for Eve? I will go first. Can I start with maybe so you were talking about the measuring the tensor scalar ratio, and I'm familiar with wanting to measure it, but I wasn't familiar with what you were specifically talking about, which is the bias on it. That was the thing you were trying to
Yes.
reduce. I don't know what this is. Can you quickly explain what you mean by that?
Yes. So I am not an expert in this area. I would point anybody who is interested in more details to this paper that explains this, but this is essentially saying What we can do with the SO-SATs alone in simulations, this is all simulations, in terms of the tensor to scalar ratios, these are iterations of simulations that would tell us where our measurement would come from for the SO-SATs. Without CCAT data helping to constrain foregrounds that would contribute to the bias in the measurement, the offset in R due to foreground contamination without high frequency information, then adding that in and seeing what that level could be. And it says that it might be as large as 1 × 10⁻³ that we could contribute to reducing with CCAT high frequency data.
It's what about reducing the systematic uncertainty on this measurement, also, I guess.
That's right. It's systematics from foreground specifically because of the difficulty of modeling this without measurements.
Bruce, do you want to go next?
Yeah, thanks. Thanks very much for the talk. Very informative. Can you go to the slide where you're discussing the neutrino mass sensitivity and constraints?
That was way up here, right?
Yeah, it was a little way back.
Not this one, right? It was from ACT.
Yeah, so this one. So
oh, this one.
No. So you've got yeah, here. This is the one. So you have you're showing velocity with respect to separation,
right?
And here we have the set of neutrino mass sums going up, and as the mass is going, so I was just trying to follow the logic. Okay, so the lower the mass of the neutrinos, the more they wash out structure.
The higher the mass of the neutrinos, the more they wash out structure, because they're taking a larger proportion of the mass budget of the universe with them relativistically.
Because they're taking a larger, because they're still, okay, so I'm just sort of trying to follow the logic.
Yeah, so they essentially take the mass. So I like to look at this plot for concept. So here's 0 mass in neutrinos. All the mass then, to make it really simple, let's just say all the mass in the universe clusters down into overdensities. But then when you put some mass in neutrinos, it free streams relativistically. So there's simply less available to cluster down into the overdensities.
All right, so there's a kind of so this is a little bit subtle, because I mean, and it's partly an effect of the limits on the neutrino mass being so good. So these masses are actually still very small as far as the neutrinos are concerned. And so it's not really the change in neutrino dynamics that's producing the change in this plot. It's the change of their share of the mass budget.
Yeah, this is solely the sum of neutrino masses. So no other neutrino properties other than the mass.
No, that part I get, but but the change in dynamics is more from, we know how much dark matter there is if you make, the larger you make the neutrino mass, the less mass there is in the dark matter proper, or the other dark matter species presumed ultra-relativistic. That's what's going on. Is that right?
Yes, I think so. I don't typically think about this in terms of other light relativistic species. I think it gets a little bit more complex when you consider that balance. But in the simple case where you were thinking of mass in dark and baryonic matter versus mass in neutrinos, it is a bit of a seesaw. So when you increase the mass in the neutrinos, you just wash out more of the structure that you see in large scale clustering because of the dark matter clumping.
All right, I'm going to have to think about that some more, but
I think
that's at least
right.
giving me the basis of the basis of the statement here. So I did have one other question while we're on that. Is this measurement degenerate or partially degenerate with any of the other quantities you're trying to measure? Because I mean, really, this is a sort of a amount of peaking in a fairly nondescript looking curve. Is that a
Yes.
question that's easily answered?
Yes, so this is one approach to measure neutrino mass sum. As you can tell from this plot, it's going to be a challenging measurement, and it is degenerate with other measurement approaches, like what I showed previously with ACT-DR6 measurements, where you're constraining neutrino mass in various parameter spaces from the CMB. So this is a complementary approach that would provide a check with a different probe, but in the same sorts of data sets.
No, sorry. What I meant was more, is this neutrino mass answer here degenerate with any other parameter you're trying to measure from this spectrum?
Oh, yes. So in the next plot, you can see a little bit of what changes when you toggle other inputs. So you are going to see multiple inputs change the shape of this curve.
Yeah.
And so piecing those apart is important. These papers go into some details about how you can do that with the shape of the curves, but it will be subtle.
Okay, thank you.
Thank you.
Yeah, I was actually also going to ask about that. I mean, even in lambda CDM, it must be degenerate with something. Is it like omega matter and S8 and stuff like this? Will these, if you're trying to do some joint fit of everything, is it
Right. So
presumably
it
you need
is.
more data than just this measurement, right?
Yes, no, this is just a complementary approach to the lambda CDM full breakdown. And in that you have many parameters that kind of go beyond the independent six that you can tune. And I don't have a quick overview of how those all work, but yes, you can tune some knobs and others will turn in CDM, lambda CDM analysis for CMB. And this is kind of just another tool we could use with the same data.
Can you also show it was a few slides before this, the like there's the observational handle you had on this, which I think you were quantifying in terms of yeah, there's P.
Oh, yes.
And you showed the plots, and I just want to understand, how does the redshift information enter here? Do you break this down by redshift, or is it just an integrated thing? Because this is at a specific redshift, that theoretical one, right?
Right, so these bins, this is just a portion, actually, like a screenshot of a much larger plot. And in the larger plot, we have many luminosity bins. So what's being shown right now is one luminosity bin with one typical redshift, although there is some spread. And then we're binning in the data points in terms of just separation alone. So we have tried binning in redshift. We haven't seen anything very compelling. We just lack the statistics to do that in a sensitive way at the moment because we don't have too many sources. So this measurement took 100,000 galaxies. When you subdivide, you just lack your constraining power. So we're excited to look into it again with DESI. We are still in the domain where we're not likely to see something within our uncertainties that already exist. But it's something we will consider. But here we've not done any redshift binning.
But how do you calculate R then? Is this a three-dimensional R, or is it a projected on the sky?
Oh, it is projected. Oh, yes, it is projected using the projection of redshift and location through this geometric factor.
Please, anyone else jump in if you have questions. I have a couple more. Maybe I'll just do one in the interest of time. So it was the plot. I think it was from ACT of it was not. It was like when you were looking at the SZ effect, but not specific point sources. I think it was like a sort of diffuse version, or one where you had some nice map you were showing. Yeah, I think it was this one, right?
Yeah.
So you're essentially looking for the same type of spectral distortion, but just not pinning it to any specific source like a cluster or something.
Yeah,
Is it?
exactly.
And then this is a fully integrated thing. Is there like is the spectral distortion that you get from this Compton scattering distinct enough that you can tell it you can tell apart if it's like a really local thing or something happening, at like recombination era, and this is actually something which is
Mhm.
happening due to it's something over the same redshift range that you get the usual S-set effect. I'm just sort of not sure how all these things get kind of disentangled.
Right. No, that's a great question. There is this thing called optical depth to reionization. So if people talk about tau as just like one tau, that's talking about that integrated depth. And then often when in this talk I was talking about optical depth, I was attributing it to individual objects. So you can study this in diffuse or individual object manners. Excuse me. It's yeah, it is a little bit subtle when you're making a Compton Y map. You're looking at integrated line of sight electron pressure through Compton Y. And so you can do redshift binning if you have redshift information of individual sources. Otherwise, it's a good question. I haven't worked with these extended maps, and I would need to revisit this paper to understand how much they, when they're making this map, what is the redshift slice and how do they determine exactly those parameters? I'm not sure with this plot specifically, but it is an integrated signal for the most part.
All right. So, yeah, I think that's all still